Let's start with our chapter 23, radioactivity. Background radiation. Definition. Background radiation equals to radiation that is always present around us from natural and man made sources. What are the main natural sources? Radon gas from rocks, biggest contributor. Rocks and buildings contain radioactive materials like uranium, thorium. Food and drink, example potassium 40 in bananas. Cosmic rays, high energy particles from the sun and space. Carbon 14 in all living things. Man made sources, medical uses, X rays, CT scans, tracers, radiotherapy. Nuclear waste, nuclear weapons fallout. Nuclear accidents, example Chernobyl. Count rate equals to number of decays detected per second or per minute. Detecting radiation, we have Geiger-Müller tube plus counter. Clicks every time it detects radiation. Higher click rate means higher radiation. Count rate decreases with distance from the source. Other detectors are photographic film badges, ionization chamber, scintillation counters. Correcting for background, measures background count with no source, then measure with source. Corrected count rate equals to measure count minus background count. Now let's discuss type of radiation, radioactive decay. Key idea. Decay is spontaneous and random. You cannot predict which nucleus will decay or when. Only the probability half-life is predictable. Nuclei are unstable if too many protons or neutrons and very large nuclei it has. Three main types. Type, nature, typical penetration, changes, and ionizing power. So for alpha particle, helium nucleus, we have 2p, 2n, charge is plus 2, few centimeter in air, stopped by paper, and ionization is very high. Beta particles, they are fast electrons, the charge is minus 1, few 10s of centimeters, stopped by thin Al, and ionizing power is medium. Then we have gamma rays, EM wave, high energy, the charge is 0, very penetrating, reduced by thick lead, and ionizing power is low. So let's discuss penetration summary. Alpha blocked by paper or skin, beta blocked by a few aluminium, and gamma reduced by lead or thick concrete. Now let's discuss ionizing power and deflection. Ionization equals to knocking electrons off atoms creates ions. Radiation can ionize atoms, dangerous to living cells, and can occur DNA damage. Ionizing strength alpha, most ionizing, large mass, charge is positive 2. Beta is moderately ionizing. Gamma is weakly ionizing, no charge, no mass. Deflection in electric field. Alpha plus 2 deflected towards negative plate. Beta minus 1 deflected towards positive plate. Gamma 0 not deflected. So alpha deflected towards negative plate, beta deflected towards positive plate, and the gamma has no deflection. Beta is much lighter, deflected more than alpha. Deflection in magnetic field. Alpha and beta are both deflected but in opposite direction because of opposite charges. Gamma is not deflected. Let's discuss radioactive decay and equation. Why nuclei decay? To become more stable. Too many nucleons means heavy nucleus, so alpha decay is likely. Too many neutron, so beta decay is likely. Too much extra energy, gamma emission is likely. Now let's discuss alpha decay. What is emitted? It releases an alpha particle. An alpha particle is the same as helium nucleus. with mass number 4 and atomic number 2. It has two protons, p, and two neutrons. What changes in original atom? If an atom is written as like this, after alpha decay, mass number decreases by 4. So minus 4, A minus 4. And proton atomic number decreases by 2. So Z minus 2. So our new atom will become, from the atomic number and from the mass number, you can see that the values will decrease, plus helium 4 and 2 will also be released, where Y is the new element formed after decay. Meaning, in simple words, the atom loses 4 particles from its nucleus, 2 proton and 2 neutron. Since proton decide the element, the atom turns into a new element. Now let's discuss beta decay. What happens inside the nucleus? A neutron converts into a proton plus electron. The electron is emitted out of the nucleus as a beta particle. What changes? Mass number stays the same, A doesn't change, whereas proton atomic number increases by 1, so Z plus 1. So the new atom becomes Y. A will not change. With Z, you can see plus 1, and 1 electron beta particle will be emitted out. Meaning, in simple word, the atom spits out an electron and an extra charge proton remain. So the element changes to the next one on the periodic table. Example of uranium decay by alpha. You'll get thorium and helium. It became a new element, thorium. If carbon decays by beta, it became nitrogen, the next element. So, in short, alpha decay emits alpha, the changes in the mass number and the proton number, and this is the general form of it. Similarly, in beta, neutron turns into proton plus electron. Electron is emitted from nucleus, changes our mass number. A stays the same. And proton is plus 1. This is our general form. Gamma decay, nucleus emits photon, energy only. No change in A or Z, only loses electron, energy. General form is this, so you can see Y00, 0, there is no change here. In all decay equation, total A and total Z are same before and after conservation. Be careful about that. Now let's discuss half-life. Definition: half-life equals to time taken for half the unstable nuclei in a sample to decay, or you can say activity count rate to fall to half its initial value. Key points: each half-life remaining activity on nuclei half again. So 1 become 1 over 2, 1 over 2 will become 1 over 4, 1 over 4 will become 1 over 8, so on and so forth. Half-life is constant for a given isotopes, independent of temperature, pressure, etc. The table pattern, for example, you can see here half-lives, and it is shown diagrammatically as well in the graph. So your initial activity, mark it as A naught, then A naught divided by 2 on y-axis, and you can make a curve, and whole in half-life can be shown as it's given in the diagram. Now let's discuss use of radiation. Choice of isotopes depend on type of radiation, alpha, beta or gamma. Half-life short, medium, long. Alpha used in smoke alarms. Small alpha source inside the detector. Alpha particles ionize air. Small current flows. Smoke absorb alpha current, drops alarm sounds. Long life, half-life source, so detector works for years. Gamma, sterilization and food irradiation. Sterilize medical equipment, Y penetrates packaging and instrument. Irradiate food, kills bacteria, longer shelf life. Source usually has half life of a few years, does not need frequent replacement. For beta gamma thickness monitoring, source below, material example paper, plastic foil, detector above. If material too thick, fewer counts, machine adjust rollers. For beta, for thin material, example aluminium foil or paper. For gamma, for very thick material, example metal slabs. Source medium, long half life, so count stays roughly stable. Now let's discuss gamma medical diagnosis and treatment. Number one, radiotherapy for cancer treatment. Narrow beams of gamma aimed at tumor from different angles. Tumor gets large dose, surrounding healthy tissues gets less. Tracer example PET scans. Radioactive substance injected or swallowed emits gamma rays detected by scanner to show organ function. Short half life hours, so it leaves body quickly. Dangers of radiation and safety. Biological effects. Ionizing radiation can ionize DNA, damage and mutation can occur, cause cell death, cause cancer. If mutated cell keep dividing, so it turns into tumor. Large doses quickly radiation sickness. Skin burns, nausea, low white blood cells, weak immune system. General safety rules to reduce dose, time, reduce exposure, use source of minimum time. Distance, increase distance, use tongues, keep at arm's length, store sources away from people. Shielding, lead concrete, thick barriers, lead aprons, lead screens, example X ray rooms. Storage, transport, disposal, keep sources in lead line containers. Record usage, who, when, which source. Transport in strong casks that can survive fire, impact water. Waste with long half life stored in sealed containers and buried deep underground. With this, we have finished our chapter. See you in our next chapter.